So we're going to continue doing our complex numbers. I'm going to skip this example because if you look, it's the exact same problem as this, except there's a 1/5 over here. So this will be 1/5 of this, which will just be irrational, 13. Oh, and then there's some different numbers here. I guess the -2, so it'll just be negative 6i and a minus I, so you'll have -7i. Anyways, let's go to the next one. So let's talk about multiplying and dividing. Before you do any multiplying or dividing, remember, you need to multiply. Outside's outside, inside's inside. This is not a FOIL. FOIL has plus between it. We'll do that later. Also, you must take out the negative square roots first. You need to put the i's in. You can't see without the i's, okay? And also, what is I times I? Well, that is I squared, which is -1. So watch what happens. We know that this is the square root of 81 times the square root of -1. Just like 25 is the square root of 25 times the square root of -1. We know this is I, square root of 81 is 9, so we call this 9i. Well, that's 9i times 25 times -1. Well, 25 times square root of -1, well, that's just 5i. 9 times 5, well, that is just 45. 45, I and I give me I squared. Now, I squared, wait a minute, we just said that is -1. So 45 times -1, it's actually just -45 is the answer here. Now, if we are not careful, we could actually get into some problems. If you multiply the square root of 81, the -81, times the square root of -25, now, I'm going to tell you, you're going to get something, right? You're going to get something big, but a negative times a negative is going to give you a positive. Believe it or not, if you square that, you're going to get a number that's going to be positive. Then take a square root, you're going to get 45. You're going to lose the negative. That's the problem. That's why you have to make sure you put the i's in, because that will create that negative you need to have. All right, over here, if we look, like right now, we can actually write this. Well, square root of -5, which is the square root of -1 times the square root of 5. It's just I radical 5, isn't it? Well, the square root of 80, well, that is going to be 16 times 5. Now, that's because I'm pretty good at my radicals, but it's -1 times 16 and 5, right? You're going to take the square root of each of those, right? Well, that's going to be times I, square root of 16, well, we call that 4, and then the square root of 5. Alrighty? So then, look, we get 4 times 1, which is just 4, and then I and I, which is I squared, so you get 4 times I squared. And radical 5 times radical 5, well, isn't that just 5? 4 and 5 give me 20 when you multiply it. 20 times the square root of well, I squared, which we just discussed, remember, is -1, which is -20. Look what happens if you just multiply them to start. You would get just positive 400. And then the square root of 400 is just 20. But you would lose the negatives. So that's what's very important here. All right, so be careful. The last one over here, if we do this, we really don't even have to simplify it. It's 5 and 2, which doesn't simplify anyways. So it's -3. Just to get rid of the negative, we just call it an I, and I have a radical 10 left. All right, and this is 2. This is I, radical 10. Well, -3 times the times sign. 2 is just -6i squared. And then radical 10 times radical 10 is 10. And then I get -60i squared. Well, this is just -1, which actually turns into now being -60 times -1, which is positive 60. Right? And if you looked, if we did this right here, we would have got -6. This would have been, if you multiply these without doing the i's, you would have got 100, and you would have lost the negative there, which would have made it wrong. So you don't want to get wrong answers. Wrong answers stink. So, one of the things we're going to talk about is when you attach a real part and a complex, or a real part and imaginary part together, we get what we call a complex number. Right? I's are imaginary. Remember that? I equals the square root of -1. But if you put adding a number to it, you now combine a real and imaginary, which is complicated. It's complex. Alrighty? Well, we like this and don't like this in some ways. One of the biggest things is you lose a big property with numbers. Okay? Complex numbers don't have an order. If you have a real and imaginary part, a plus bi is the form we call it. You have the real and the imaginary. All right? You add them together and you get complex. Okay? Their symbol is a C with a line through it, not like a cent sign. Okay? And it is the biggest set we actually have now of numbers. Makes our system we work with field actually, which is kind of cool. All right? But we lose order. So here's some complex numbers. 3 plus 4i, 2 minus 6i, negative 4 plus 8i. We always like to put the imaginary later. Well, we don't know which one's bigger, 3 plus 4i versus 2 minus 6i. Maybe there's 7 there, but who knows? We don't know what it's actually going to do. But we can graph these things, which is nice. So we have right here, we normally have an xy axis, but now we're going to change this axis. We're going to call this the real axis. That's the left and the right one here. Okay, the a-axis, or x, as we usually call it. The up and down axis is the imaginary. That's the bi axis. So if we graph, believe it or not, our complex numbers can be graphed real, then imaginary. They give us points. So to plot the complex numbers, we need to consider any complex number, by the way, where b equals 0, that means this goes away. It's just a what number? Well, you just got the real part. Okay, because the imaginary part is ruled out. So it's going to be on, guess what axis? The real axis. On the other hand, if the a goes away, okay, we have what we call a pure imaginary. There's no real part. All right? And then any complex number of a plus bi, or a and b is actually a complex number. And like I just said, the horizontal axis we're going to call imaginary, and then the number portion will be the vertical. So if we graph, again, I have x and y, you can call it a and bi, that's what most people do. This is just telling us the direction on the a-axis, so left and right, and then this is the up and down. So if that's the case, if I want to plot negative 3 plus 4i, you go, here's my origin, negative 1, negative 2, negative 3. That's the real part, and then 1, 2, 3, 4. Right there is negative 3 plus 4i. Now if I look 0 plus 2i, that's 0 over and then 2 up. 0 plus 2i. Notice how it's on the imaginary axis. Just an imaginary number, like we should. On the other hand, if I go negative 3, 0, right here, 0i, I'm on the real axis because negative 3 is a real number. Then last but not least, you can see we have 2 over, because it's 2 in our real axis, and then 5 on our imaginary. 1, 2, 3, 4, 5. Right there. This is 2 plus 5i. So again, which one's the biggest, which one's the smallest? I have no idea. We lose that order principle. Right? And the coordinates of the origin still is 0, 0, so it's 0 plus 0i. Now, why do we want to deal with this? Okay. Well, we like to call something that's very popular in mathematics and physics, we call them vectors. A vector is actually what we use complex numbers for. The points that we made have a direction and a magnitude. Vector, just like in one of those wonderful movies, you should know what it is. Vector, because I have direction and magnitude. Okay? Well, all of these have the same thing. So, for example, if you go 3 meters this way and 4 meters north, how far did you go total? That's a 3, 4, 5 right triangle, so that's 5. So that's where I get the 5 from. How do we use this? This is Pythag. Well, what's interesting is sometimes we like to display these as vectors. Well, the same vectors can be displayed. We know how to graph these, so negative 3, 4i is right there. But a vector has a direction and a magnitude. So the point makes the direction. They should be straight. And the length of this is its magnitude. So sometimes we want to order things in magnitude. That we can do. So like here, the second one, we'll do it in red, is -2, or 0, -2. So 0, -2, that's down here. That's the vector here. We put an arrowhead on it so you can see it. 0 minus 2i. All right, if I do the next one in green, 3 over, 0 up, 3 over, that's 3 plus 0i. And then the last one, 2 over, 5 up there. There's the dot we graphed. And there we go there, which is 2 plus 5i. Right, and that's how we graph vectors. Right. So the magnitude is the last piece of this, which you can see is the distance of those things. It's the Pythagorean theorem. Remember, this is my a and this is my b. So a squared plus b squared equals c squared, right? Now you have it equal to c. You square them both, don't you get the Pythagorean theorem? We're just looking for that distance. We use the Pythagorean theorem. So what's nice is the magnitude, which is denoted by these absolute value bars. That might mean something later on. We can find. So like here, isn't it just -3 squared plus 4 squared? Ignore the I with magnitudes. And you're going to see that. We get that as 25, and you take a square root, which is 5. So the magnitude is 5 units. Over here, we can do the same thing. This is just 2 units, and this is 3 units at a time. And here, it's 2 squared plus -5 squared. You're going to always get positive numbers here. So that's 4 plus 25, which is the square root of 29. So you can see that's the biggest vector. So you can see we can do a lot with these things in other math fields. And vectors are very, very important, especially the physics. Talk to you guys later.